and brother and I would be in the back seat. We'd be typically fighting about who gets to play with the Game Boy or the Game Gear, or maybe whoever gets to eat the last bag of chips. My brother was older, so he would win. And typically, road trips were just such a great experience for me. And more recently in my life, also some really wonderful road trips with my family, and we did some cool stuff across the US. There's one thing that on these road trips that really can cause some problems. And it's a nice big detour sign like this one. You're on a road trip, you're feeling great, the sun is shining, the wind is perfect, and lo and behold, you run into a detour sign. John, when you see that detour sign, what do you usually think about? Okay. So yeah, you might think there's construction, but usually there's almost like a bit of an anxiety that sets in, which is what I want Sean to say, and he didn't, which is unfortunate. But anxiety that now there's going to be a delay, my trip is really messed up, and now I'm stressed, right? That's usually what happens to me, at least. But that being said, you see a detour sign like this, maybe it's held by a police officer or construction crew member. You're going to usually comply with it, take the detour, and go on your merry way. Imagine for a second, though, this guy was holding up the detour sign. By the way, this was an AI-generated image, kind of nice. But this guy is holding up the sign. Are you inclined to take that detour? I'll tell you guys right now, as much as I'd like to portray myself as a tough guy, I would be running the opposite way as fast as absolutely possible. Faster than George Costanza running out of this burning fire. For those of you who've seen this Seinfeld episode, it's absolutely one of my favorite scenes. But in any case, I wouldn't be taking that detour. I'll tell you that right now. And what it comes down to is we're going to, as we look through tunnel crack and talk about some of the technical details, the decision made by, I would let you watch this over and over, and I'm sure this would actually be the best presentation you've seen, but I've got to skip that. But tunnel crack and some of the vulnerabilities we're going to talk about take advantage of inherent trust under the hood, similar to that of the inherent trust that we see with this nice, fancy, official detour sign. So we're going to get into the details, and hopefully you enjoyed that little introduction. All right, so super quick agenda in favor of time. We'll do a quick intro, explain who I am, why I'm here, all that good stuff. High-level introduction to remote access technologies in general. We're not going to go super deep into any of that. Then we're going to talk about this category of vulnerabilities called tunnel crack, get into the details. I also have about 10 minutes of demonstration to share along with that. And then time permitting, chances are we're not going to get to it, but I will do my absolute best. Some just general best practices and lessons learned from my experience in securing remote access infrastructure and remote access technologies. Oops, we skipped to the very end. So that was great. By the way, I'm borrowing someone's laptop, so it's actually kind of interesting that would happen. I'm going back to the beginning. All right, sorry about that. I mean, you're not like controlling the laptop from all the way back there, are you? Sabotaging? All right. So who am I? So currently I'm a systems engineer at Palo Alto Networks for the last 16 months. I was also a consulting engineer at Palo Alto Networks. So working with companies across North America, specifically in remote access, zero trust network access to be specific. Companies of all sizes, organizations of all sizes, just working with them to figure out a whole variety of best practices in implementation and operations. Experience primarily in the networking and networking security realm, more specifically and more recently application security as well, which has been a lot of fun. Hobbies include gaming. So I'm a gamer when I have the opportunity. My son is actually in the room, which is kind of a fun little tidbit of information. He's a little bit shy. But I would be remiss if I didn't say there was a wonderful game that was launching today. It's the remake of a fun game that I used to play as a kid, Super Mario RPG. And I wore these awesome Mario socks to embarrass my wife, as you guys can see. Is a little bit of an honor to that. I love sci-fi, books, TV, movies, and hockey as well. And this is not a sponsored talk, by the way, or anything like that. So everything that I'm just talking about and all of the information is purely my own, not of my employer. All right, now let's get into the details. So as I said, a high-level intro to remote access technologies. So I developed this quote all by myself, so it's pretty thought-provoking. So what is a remote access technology? The technology which provides access to servers, devices, and/or applications residing in a location to users or devices located anywhere. Very simple, but a big brain quote there that I put together. Hopefully you all enjoy it. Now, the types of remote access, very simple, high-level overview of the sort of broad categories. Remote desktop style solutions, virtual private network solutions, as well as more recently, zero trust network access solutions. Tunnel crack and some of the specifics to that are going to be much more applicable to both virtual private network and zero trust network. So I'm going to be kind of omitting the remote desktop solutions, but it was worth pointing out for the sake of completions. So what is a virtual private network, or VPN? It's been around for a very long time. I'm sure a lot of you are very familiar with this already. But the concept is quite simple. You want to extend a network to somewhere else. That's quite frankly what it is. Commonly used under the hood, using protocols like IPsec and TLS to create a tunnel of some kind. Very common to leverage this type of technology to enable privacy over some insecure medium, whether that's a guest wireless or a local area network maybe that you just don't trust, like in a hotel, for example. It's typically, I guess fundamentally the way it behaves is it's very all or nothing. Once you're on that network, once you've established this VPN, you're sort of, it's almost like teleporting your laptop or your machine to the other location, meaning you're now on that network with unlimited access, fundamentally. You could implement other controls at a different location, but that's sort of outside the scope of how a VPN operates. It's detached from that. So very simple. And by the way, the 5 or 6 or 7 slides that we're going to talk about here about these types of remote access solutions, it's meant to be very high level, just to make sure we all have the same basic context. But we'll be getting pretty deep into technical context here right away as well. So if we look at this very nice, simple drawing here, we have a user, some client on the left. We have a VPN concentrator here, kind of located in the middle-ish. There's the internet, of course, that we're transmitting over, and some fancy applications on the very right-hand side. So the client's going to, of course, create a connection and authenticate to our concentrator. Nice and simple. After that, our concentrator is then responsible for assigning an IP address, subnet, DNS, etc., to our client. So now it's at that point, after that first 2 steps have established, IP packets from that user, that device, are now going to be targeting this VPN concentrator to join this network over here, whatever that is. And as a result, the client can access these 2 applications. Everything's great. So very simple, very high level. Now, zero trust network access, kind of an evolution of the same concepts that I just talked about. Extends that enterprise network to another location. However, of course, the difference and why this even exists is we now take that concept but ingrain zero trust principles natively into that solution. That's really the big difference here. Under the hood, though, and why this is even something I'm talking about, is that we may be using tunnel-based technologies, and they may be susceptible to tunnel-based vulnerabilities, similar to that of a VPN. Now, major difference, like I've already talked about, we're using fine-grained identity and context-based controls to perform all of the validation of the end user, their device, before they can actually get on to the network. And instead of teleporting your machine or your laptop over to this remote location, Instead of doing that and just allowing them unfettered access, it's almost like saying, hey, I'm going to teleport your laptop over here, but only going to plug it into this one application, and that's it. So it's a very fundamentally different architecture. And key there is explicit access. So revisiting these nice, simple diagrams. Of course, the client, similar to the last diagram, we're going to connect to this ZTNA device, whatever that may be. Some sort of assessment is going to be performed against the device, whether that's based on the user, the device, a combination of the two. The client is then going to be permitted access to a set of resources based on who they are, what they should have access to. So think about it as somebody in your HR department. They might need access to HR related resources, but other users in the organization probably don't. And then rather than trying to provide access to everything, let's limit the scope. So you can see here the client has access to the application number 1, but inherently doesn't have access to application number 2. Very straightforward. Again, VPN, you can think of it as VPN plus zero trust fundamentals ingrained into it. All right, so that was a bit of a simple high-level overview of VPNs, remote access, zero trust. Next up, we're going to talk more specifically about tunnel crack, what this vulnerability is, how it works, and then, of course, we're actually going to get into a cool demonstration. So what is tunnel crack? That's the first question we're going to have to answer. And what it is quite simply here is it's a combination of 2 widespread vulnerability. And I pointed out, or I bolded widespread because it's very, very widespread. It's a vulnerability class mostly in tunnel-based remote access technologies like VPN and zero trust, like I just shared. What's interesting is every single VPN product on the market today is vulnerable to this, at least on one OS or another. And the root cause of this stems all the way back to the real fundamentals of tunnel-based technologies, all the way back to 1996. And that's what I've quite frankly found a little bit more interesting about this vulnerability, is that it is so ubiquitous. It covers, like I said, every VPN product on the market, and it's been around for so long. It's sort of so fundamental to how these things work. It's just been kind of hiding there all along, which is kind of interesting. Now, the vulnerability itself, when it's exploited, either of the 2 vulnerabilities, the net outcome is really to take the user's private traffic that should be going over this virtual private network, taking it out of the tunnel and sort of spitting it out on the local area network. That's the root outcome that this vulnerability aims to achieve, is effectively to hurt the privacy and the security of the user. And so we're going to see that in a little bit more detail. It would be a bit of a fail on my part if I didn't recognize that this class of vulnerabilities was discovered and disclosed by this group of individuals at the bottom. I had absolutely nothing to do with that, as much as that would have been kind of cool. However, they did a great job of dissecting this and sharing this information. I've taken that information they've shared, I've packaged it up in a different way, created my own demonstration, and I'm sharing that onwards with all of you. So when I said it was ubiquitous and this was applicable to most VPN products, this is the chart specifically for one of the vulnerabilities. As you can see, every single iOS VPN product today is vulnerable to the one vulnerability in tunnel crack. Mac OS, most of them are. Windows, most of them are. Linux and Android, a little less so. So you can think about that. That's pretty significant. That's a bulk of endpoints and agents out there on the internet that are inherently vulnerable to this attack technique and this vulnerability. So we talked about tunneling a little bit, but just to be more specific and make sure we're all working from the same context here. When a device has a VPN or zero trust network access client or agent installed on it, in almost all cases, you're going to have something called the virtual adapter installed on that machine. Now, the purpose of that virtual adapter is effectively to direct packets to the far end of the tunnel. That's really ultimately what it's for. The reason for that, of course, is the operating system needs some logical construct on where to send all these packets to. And ultimately, anything that goes into the virtual adapter goes all the way out to the other end, basically, like I said earlier, almost like you're teleporting that device and all the packets from it. And then ultimately, of course, the purpose of that is to provide the security and privacy associated with those layers of encapsulation and encryption. So here's a little bit of a drawing that I put together. You can tell I'm not really an artist, and nor did I claim to be. But the simple drawing here, it's a laptop on the left-hand side. You can see I drew a little orange virtual adapter indicated in the laptop. So that's the operating system's way of recognizing and seeing this tunnel or this agent. And then the orange dotted line is effectively the tunnel that takes this user all the way from where they are today through the internet or through whatever WAN or LAN to a tunnel endpoint on the other side. So anything in between that point and this point should have absolutely no clue what this device is trying to do as far as these packets being sent through. This guy could be trying to access eBay or a bank, but anything in the middle should be completely unaware of what's happening. And that's the whole purpose, right? Privacy, security. So why do we care? Well, all of that was just a tunnel, right? Well, what's the purpose of all of this? Well, one important point here is many architectures, security inspection technologies are actually deployed over here on the far end side. So think about like web control, anti-malware, basic firewalling controls. If all of that is over here, then this path is actually quite important. It's important for me to make sure that that guy over here or this girl over here can actually get all the way over here, because I want all these security tools to do their job. Similarly, privacy, right? We talked a little bit about that already, but the user who is leveraging a VPN, maybe they don't work for an organization. Maybe they're just using a VPN purely for privacy related reasons. If I'm on Starbucks Wi-Fi, I don't want Starbucks knowing what I'm doing and why. I just want to go to NHL.com without anybody looking at what I'm doing, and that's perfectly fine. All right, so now we'll get into more specifics. So a typical adversary in the middle attack. Now, if I just go back to this picture for just one moment, if I was an adversary in the middle here, and I use whatever technique I wanted, DHCP, DNS, ARP, ICMP, a rogue AP, doesn't really matter what I use. If I'm using a VPN to go from point A over here to point B, and the VPN connects successfully, the expectation as me as an end user that privacy and security are in place, and I can feel relatively comfortable that I don't really care what's going on in the middle here, to a certain degree. Now, the challenge with that is, okay, if I'm an adversary and I want to perform one of these adversary in the middle attacks, well, I don't get a whole lot of value out of my attack. The user's using a VPN. A lot of what I'm going to see is basically just VPN traffic. I don't know what's in it. I don't know why they're using it. And that makes it very challenging as an adversary. So the techniques that I'm listing on the screen that I just described, they're all significantly hindered by this user leveraging that VPN. So us as users, as people who want to maintain security and privacy, VPNs are a great thing. For the adversary, not so much. So what if, from the adversary's perspective, we could enhance that adversary in the middle attack? What if we can make it better? What if we can actually get something out of this VPN traffic? That would be kind of good, right? From the adversary perspective, of course, putting on the scientific hat. And the reason, of course, that they may want to do that, maybe they want to do a phishing attempt, some form of credential theft, some data manipulation, content injection, some form of replay attack. reconnaissance, for the purpose of blackmail. A lot of good reasons I might want to do that as an adversary. So why don't we explore that? Now, blocking, one answer or one thought process might be, well, why don't we just block their VPN? We care so much. We see a VPN's happening. Let's just block whatever they're trying to do. And that is a reasonable approach. However, of course, a sophisticated user is going to notice that their VPN is not functional. I know I do. First thing I do at any public or insecure local area network, I'm going to fire up my VPN. And once it's established, I have some level of a fuzzy feeling inside that, okay, I'm sort of secure, right? Like I have a better feeling about all this. Without that, though, I don't feel so good. I know that I'm subject to whatever is going on this insecure network. And in addition, even if the user themselves isn't very sophisticated, the VPN software or the agent, in many cases, also can be made sophisticated enough to recognize that it's being blocked, and in that case, restrict all access. So blocking is one option, but that's not quite good enough. Instead of blocking, what if we could silently bypass the VPN tunnel from the end user? That sounds a lot better. If I could tell you, Sean, right there, that guy, that I can see you're probably going to TD Canada Trust. You're probably a customer of theirs. And any traffic that's going out to TD Canada Trust from you, I'm going to force it so that you send that out your local adapter instead of the tunnel. To me, as an adversary, if I'm playing that hat or role playing as an adversary, that sounds pretty good. And so let's explore that. And so that would be my face if I was the bad guy. So there's a Christmas theme mixed in with a bit of a devilish grin. So fundamentally, and as I talked about at the very beginning of the presentation, and by the way, anybody who missed the opening slide introduction, I apologize, but some of this may not make sense. But Tunnel Crack aims to take advantage of that inherent trust in two ways. The one, the inherent trust between the client or the VPN adapter and the local area network. That's called the local net attack. And the second is the client and the remote termination point. So if you remember the diagram that we had up, there was a device over on the very far end side. That was the tunnel termination point. That's called the server IP attack. So way back to the beginning of the presentation now, we saw the detour. And now making this relate back to that, we're taking advantage of that inherent trust. See the detour sign, see somebody with some level of authority holding it up. We're probably just going to follow suit, right? However, for us, with a bit of intuition, we saw somebody who looked a little nefarious, and I sure as heck wasn't going to follow that detour. However, our laptops, our machines aren't going to discriminate in that way. Somebody tries to make us detour, they're probably just going to go along with it. So let's get into the local net attack more specifically now. And this is a fundamental. By default, in most VPN clients, ZTNA clients, traffic or packets sent to the local area network are going to be omitted from the tunnel itself. Fundamentally, that's just for ease of use, right? If you have a printer sitting beside you or a phone or maybe a PLC or something like that you need to connect to, why would we want to send that through the tunnel? We need to access it because it's right here. So this is very common. So how could we take advantage of that fact and turn that into something we can use from the adversary's perspective? So ultimately, hey, can we selectively circumvent that tunnel? And how we do that, it's quite simple, and that's why I kind of was very fascinated by this. It's quite simple and straightforward, right? What I'm going to do from the adversary's perspective is I'm going to assign the client a public IP address and subnet, and the result, you might ask, well, okay, that's great, but why? That doesn't do anything. Well, it does, because if I can control what IP address and what subnet you're on, that means I can control what you interpret as being on the local area network. So think about this for a second. If the VPN client or the agent thinks that acme.com, that domain, actually is right beside them, well, they'd have no reason to use this tunnel, would they? They would just send it over there because they're on my network. So therein lies the way and the method of how we can circumvent our tunnel. So to set the stage and give you a little bit more of a visual form factor here, we're in a coffee shop. Common to use a VPN in a coffee shop. I know I do. The attacker first has to execute some form of a adversary in the middle attack, whether that's DHCP, rogue AP, etc. In this case, they're going to use a rogue AP. You're going to see Starbucks Wi-Fi. They're going to log in. Fantastic. You think because it's connected to your VPN, you're safe. Doesn't matter if it's a rogue AP. I've got a VPN, right? That's all good. So what the attacker does, since they control the AP, they control DHCP. And you can see over here, acme.com has an IP address of 23.93.76.124. So as an attacker, very simple. Okay, great. I want to intercept traffic to acme.com because I know that acme.com has a lot of cool PII, and whatever somebody's going to interact with that site, they likely are going to type in a credential that I like and I want. So I'm assigning an IP address to that local client of 23.93.76.0/24. Connect the dots and you see acme.com now is in that subnet. So from the perspective of the client, that's local. Okay, great. That's step one. That's good. So the client is still going to connect to its VPN concentrator over here. It's going to connect. Client's happy. Sophisticated user like myself, sophisticated, is going to connect. They're going to be happy. I'll see my VPN as a green check mark or something. I'm going to feel great. I'm secure. I'm smart. However, when the client attempts access to the target destination, acme.com in this case, what do you think is going to happen? Going to go direct. So our adversary over here has caused the traffic going to that destination to be leaked out directly to the local area network. Meaning it's no longer subject to all the encapsulation, encryption, confidentiality, integrity of that tunnel. And it's just going out to this guy or this girl that happens to be an adversary. So that's not great. As an end user, I don't really love that. What's worse is any IP address is subject to this attack. There's really no limit to what IP address is in scope. As an adversary, you could cycle through a whole long list of IPs and subnets if you'd like. If I was sitting on this rogue AP for long enough, wait for a user to connect, listen for the first few packets they send or the first few DNS requests, and that gives me enough information to know what they were trying to do. And then now I start spinning up DHCP pools for those users, put them into this subnet, start intercepting their traffic, and away we go. So I could pick a popular bank like I did with my example with Sean, or wait as I just described. Even worse, there's nothing technically stopping me from assigning a massive subnet like this one right here, 128.0.0/1. That would be representative of half the internet. So I could assign that to the end user, and they could think that entire subnet was local, effectively bypassing the tunnel. So this works. That's functional. So that's the local net attack, and I actually have a demonstration we're going to go through. We're going to talk through some more specifics. Now we're going to get into the server IP attack. So as I mentioned at the beginning, tunnel crack is a a bundle of two vulnerabilities. We talked about one already. The second one takes advantage of that inherent trust, just like the first one did. And the way it does that is by leveraging the far end destination of the tunnel. So if you think back to the diagram I showed many slides ago, there was a tunnel, a VPN concentrator or tunnel termination point over on this side. So the packets I send to that device, by design, I can't send those through the tunnel because the tunnel doesn't exist if I can't actually reach that destination. So we take advantage of the fact that in most cases, the client is going to reference that far end destination via a DNS name of some kind. So for example, let's say that VPN over there was vpn.com. So that means I have to resolve vpn.com, and we can maybe manipulate that a little bit. So what if we decided to spoof the DNS response and force traffic outside the tunnel in a nice creative way? So we're going to revisit our favorite coffee shop that apparently has an adversary just sitting there every day. So same thing. The adversary has to have established a rogue AP or DHCP adversary in the middle attack. The spinning AP in this case shows we've done a rogue AP. Now, when the clients successfully connect, what we do is we assign a malicious DNS server. So we could do simple DNS spoofing via a DNS server locally or out on the internet somewhere. It doesn't matter. The IP address in this case doesn't matter what IP I assign to the client. You saw in the first vulnerability, it did matter. That was core to the vulnerability. In this case, I don't care. So 192.168.0.0. Now, the two kind of key pieces of information here on the right, we have the VPN. This is what the client wants to connect to, 198.18.4.1. And then I have my trusty acme.com again, 23.93.76.124. So what the attacker is going to do is when the client tries to do DNS resolution against this VPN.com, I'm going to spoof the response. I don't want that to resolve to this 198.18 address. I want it to resolve to the 23.93 address. So the client performs its DNS request, VPN.com. DNS server, in this case, is compromised. It responds with 23.93.76.124. And as a result, the tunnel, in this case, we're going to allow to be established. So the attacker has to have a little bit of technical capability, of course. They're going to do a destination NAT effectively. All the traffic on certain ports going to this IP address is going to get destination NATed to this IP address. But the traffic we're interested in, we're of course not going to do that. So what happens here is requests for the acme.com website now take advantage of that trust relationship, and they're going to just spit out locally on the local area network, and they're going to be observed, of course, by this attacker. So I have a demonstration specific to this, which will hopefully make this more clear if it's not. But effectively, we're taking the trust relationship created by the IP address of the tunnel that we're connecting to. In this case, we're manipulating and spoofing the IP address of that tunnel. And anything sent to this by default can't go through the tunnel. That's just fundamentally the way the VPN is going to function. So we can't send it through the tunnel, and we trust it. So let's not send it through the tunnel. Let's send it direct, which is exactly what happens. So continuing with that, same concept here of the local net attack. By using this, we can potentially force any domain or website to bypass the tunnel, which is exactly what we just saw on that previous slide. We can choose a high-value target domain in advance, similar to what I did with Sean and TD, and or of course we could wait and see traffic and pick one of our choosing. Okay, so let's try it out. I've talked a lot. I'm ready to show something now. And I'm sure you guys are all ready to see something. Right, Quinn? He's not ready. But we're going to get him ready. So what we're going to do, we're going to showcase both vulnerabilities. First and foremost is the local net attack. So we're going to do an adversary in the middle attack with Kali Linux. We're going to create a rogue DHCP server. We're actually going to use a tool called DHCP pig to exhaust the legitimate DHCP server that may be present already. The reason for that is, of course, if you have two DHCP servers running, it's basically a race condition. So I want to exhaust that one, so it's not even a bother for me anymore. So I'm going to use DHCP pig to do that. And at that point, I have control on that network of all the IP and router and DNS assignments. So that gives me a ton of power. But because this user that I'm attempting to compromise is using a VPN, I've lost some of that power and I want to take it back, right? That's what the adversary wants to do. So the question, and what we're going to try to do, is can we force acme.com to get outside of the tunnel, the VPN connection? And that's, if I made a successful demo, then you'll know it's successful based on that outcome. Same concepts here with the server IP attack. We're going to use rogue DHCP server, use DHCP pig again. This time we're going to take advantage of the DNS and router assignment. We're going to look for the presence of a tunnel or a VPN connection in some way. Then we're going to do the DNS spoofing with DNS chef. And then the question remains, can we, again, force traffic outside the VPN tunnel? All right. That means it's demo time. That means, and by the way, this I was briefly considering doing a live demonstration, trying to go whiz through everything and impress everybody. But then I thought, you know what? Something will absolutely go wrong. And I want to get home and play Super Mario RPG tonight. So I got to make sure this goes well. So I'm going to take a Ludens here just to soothe my throat. And I'm going to go ahead and play the first demo. And I'll be talking through it, and hopefully it comes up okay-ish. I know it's not going to be perfect. All right. So the scope here of the yeah, it's a little small. I apologize, but hopefully the essence of what I'm describing is there. So I'm going to go back to the beginning just so I can talk through this. So I've got two things happening here. I've got, first and foremost, my Windows 10 client that you're seeing right here. And then I've got a Kali Linux instance that I'm also going to be swapping between. So the first thing I'm showing you here in this demonstration is the IP address of the local client. You can see it's right now 192.168, blah, blah. Not important. In addition, the VPN connection also has a 192.168.30.x IP address. There you go. That's what I'm highlighting there at the top. You can see I'm also highlighting the gateway and the DHCP server of the VPN adapter. I'm going to do a trace route to an internet destination. And you can see, hopefully-ish, the next hop is the VPN adapter, 30.1. I'm going to do a route print just to show this is the state of the routing table. What's important to note here, two things. One is I have a default route on this machine. It's pointing me out to the 30.1 gateway, which is the VPN. And right below it, I have a special route, which I'm not going to talk about right now, but that'll be relevant to the server IP attack. Okay, so also, this is just the baseline. On the bottom there, I'm just showing you, I'm using an open source software called Soft Ether for the VPN. And right now it's connected. Okay, great. Nice and simple. I'm going to go to the acme.com. And with a little bit of patience, acme.com will load. And everything's great. Acme.com looks good. It's very clearly in a very old website. I'm sure some of you have been here before. And I'm also showing certificate is there and it's normal. Nothing strange has happened. Okay, great. So user can do what they want to do. Everything's secure. Everyone's happy. Now, apologies again, this is a bit small. What you're seeing here on my Kali box, first and foremost, a bunch of secondary addresses on my Ethernet interface. Those will become relevant in a moment. You don't need to worry about reading them. First thing I'm doing, if you can remember the little script that I wrote up, I'm going to do a DHCP exhaustion attack against that local network. I'm using DHCP pig. Let's eat up all the DHCP leases. So there you can see it's running. The outcome here in just a moment will show up that the DHCP pool is exhausted. And then me as an attacker, I know, hey, that's great. Now I'm going to fire up my own rogue DHCP server. All right, so DHCP pool exhausted there at the bottom. Loading screen, okay. Next up, just doing a simple curl command here. If it loads. There we go. So curl, the reason I'm showing you this is I'm running an Nginx server locally on this machine, and it's presenting a forged malicious version of the Acme website. So I just did a curl to the loopback address. Now I'm running DNS chef. DNS chef, again, there's a command that allows me to do DNS spoofing. In this specific attack, it's actually not that important to do any DNS spoofing. However, I'm doing it because there are certain destinations and domains and websites that you might be going to that actually respond or resolve to a whole list of IP addresses. So if you did an NS lookup to rbc.com or one of the large e-commerce websites, you're likely going to get a whole bunch of different IPs that come back. The reason I'm doing this in this attack is just simply to force resolution to always be that address. So I can sort of coax the user to always be referencing that address in that subnet. All right. Now finally, I'm going to boot up my rogue DHCP server with EtherCap. You can see I'm putting a DHCP pool for the 239376 subnet, like we saw earlier. And now the magic is finished on the back end side. So I'm going to do a release renew on the client. This would be very analogous to a new client joining the network that you're perhaps trying to compromise. So we're going to wait for that to spin up, and if this works, what we expect to see is a public IP address assigned to this client. So you can see there, Ethernet 0, I've got an IP, 2393, etc. You can see I've got my default route pointing out that VPN adapter. Now I'm going to boot up my VPN connection. And any luck, it'll connect, and there it is. All right, so VPN's established. The client currently has a public IP address assigned to it as part of the attack, like we saw earlier. So that's all looking great. Now we're going to do a route print just to see what current state is. You can see there I'm still using the VPN. There's a default route out the VPN adapter. Nothing's changed as far as that's concerned. I'm going to do my trace route out to the internet, still using the VPN path. So from the end user perspective, it looks status quo right now. Everything's the same other than the IP address assigned to the desktop. However, when we go to acme.com, things start to be a little bit broken. Reason for this, of course, is my own error, and you're going to see me kind of scramble and panic as I'm recording this. The Nginx instance that I'm running is only listening port 80, and I was trying to access port 443 on the last page. So I recognize that, and you can see my scrolling everywhere. So I go http acme.com, and now I've got an Acme Bank fake website. So if I was, of course, a little bit more polished, I could create an identical replication of the existing site, throw in some additional content that the user would likely interact with. So you can see that's a local net attack in a nutshell. Yeah, absolutely would have been. Yep. Correct. Yep. No, you're absolutely right. I'm gonna hold off on answering that for just a moment, but it is something I will address because it's very relevant. Yeah, you don't mind. All right, so the last piece of this local net attack that I'm just walking through is in the soft ether client. Since the vulnerability was disclosed, the people who developed this product released a mitigation to this attack It's called the tunnel crack protection. You can see it's a nice little simple checkbox. So in the soft ether client, I enabled that checkbox. Now I got to restart the client, and I'm just going to run through this exact same attack from the client's perspective to see what happens. So you can see I'm connected to the VPN with that flag set. And now I go to acme.com, and in this case, I'm actually just blocked. So the way that the mitigation that was implemented by Soft Ether is very heavy-handed. Basically, anything on the local area network, the VPN client is not going to let you talk to directly. So that's their mitigation. Again, I said that was a heavy-handed approach because if you have legitimate reason to access something on your local network, now that's broken. So you can imagine the executive of a large oil and gas company now who can't print locally or can't connect to their big TV that they stream to or something. They're probably not going to be all that happy with that mitigation, right? Okay, so that was the local net attack. And quickly running out of time, so I'm going to zip through this demo and wrap up. So I might fast forward just a little bit in your interest of time. So this is the server IP attack. Again, the second vulnerability. What I'm going to showcase here very quickly, client again is connected to an IP address, or rather, client has retrieved an IP address that's completely irrelevant to this attack. In this case, it's 172.16. I'm showing that the tunnel crack protection has been disabled. It's not relevant to this client right now. We're going to do a trace route just to show what path this traffic would take. It's going out the VPN. The 30.1 is our next hop. That's all great. This is working as expected in the moment for the end user. What we're going to point out here now, this time though, more specifically, is two specific routes on this endpoint. First one is that default route, which matters. But the second one that I didn't talk about in the last demo is this very specific IP address, 20.66.47.237. And that's what tunnelcrack.KyleMcKay.ca resolves to. So that's the real IP address. And you can see just by the output of that routing table, that's treated specially, right? That's a special address that I don't want to send traffic through the tunnel. So that route exists purely for the purpose of steering that out of the tunnel, keeping it local. And that's there for very legitimate technical reasons. All right, so we'll go to acme.com. This time we'll use an incognito window, just make sure we get no cache. You can see everything works great. All right. So we jump to Kali, fast forwarding just a little bit. So what we're going to do first, we are going to set up our DNS spoofing with DNS chef. Important to note, very simple command, very simple syntax. I'm not going to go over everything. But basically, I mark a domain, so tunnelcrack.KyleMcKay.ca, and then I mark a fake IP address. So I pick whatever I want that domain to resolve to. So I've picked the IP address of acme.com, and I picked the domain name or the VPN endpoint itself. Slide it over that. All right. I've started the DNS chef. Now you'll see I'm just doing a simple NS lookup to show what acme.com resolves to, which is that same address that I showed on the previous command. So nice and simple. All right. Now we go back to the client. We're going to disconnect their VPN, reestablish, do a flush DNS first, of course. Do a DNS lookup, or NS lookup in this case, of tunnelcrack.KyleMcKay.ca. You can see it resolves to that malicious IP or the spoofed IP. Now we'll actually connect. And then when we do the route print, you'll notice when we compare what we saw previously to this, that special route that I talked about, that /32, it now is 23 23.93 instead of the original 20.66 or whatever it was. So with that simple change, this is effectively the vulnerability in action. That simple routing table change that I was able to coerce the client to make is effectively the server IP attack. And you can see in this case, I've decided as the adversary, I'm going to add that IP address on the local machine so I can intercept traffic going to the acme.com website, and I can serve up my own version of it, just like I did previously. So I'll do a trace route to that server IP address. And you can see one hop away. It's should be on the other side of the internet, but I'm seeing it as one hop away now. Interesting. And the same idea, go to acme.com, and now I get the forged or malicious version of the site. So fundamentally here, taking advantage of that inherent trust between the client and the far end server IP. And in the previous vulnerability, we took advantage of the relationship between the client and its local area network to do pretty much whatever we want. In this case, I decided to present a phishing website, but that's just the tip of the iceberg. Next step here, I just showed tunnel crack protection, but I'm just going to skip that. So I'm going to conclude here with a couple quick slides, and then we'll get out of here. So we saw the local net attack. Requests for acme.com were compromised, sent outside of the tunnel. Big check mark. I accomplished my mission. I'm happy. We used, of course, the public IP DHCP assignment to the endpoint as part of the manipulation and the coercion. Server IP attack. We used a spoof DNS response in order to bring that traffic outside the VPN tunnel. That was another big check mark. That was successful. And then I also showed, in at least the initial case, the soft ether tunnel crack protection was enabled, and it successfully mitigated that attack. Now, possible mitigations. Of course, if your VPN software has an update available introducing protection, that's probably the best course of action. For the local net attack, though, it's very difficult to fully implement because we don't know if it's legitimate or not to talk to this local network. So the best mitigation is likely that if a local IP address is assigned and it happens to be a public IP address, that should really be the warning flag or the red flag that says, hey, this is unusual, and we probably want to limit access to the local area network in that instance, as opposed to the heavy-handed approach like this, what I'm showing on screen, which is to basically say, hey, let's block everything to the local area network, because the CEO is going to call and say, hey, I need to talk to this printer. So that proceed with caution on that mitigation, simply because it's very heavy-handed. Now the server IP attack, extremely difficult to mitigate, simply because we need to talk to that far end destination in order to actually establish the tunnel. So I can't break that. The best course of action is likely application aware enforcement. And that gets implemented down at the software level, where instead of allowing anything from the client operating system to talk to that destination IP address, I just allow the VPN software itself. So if a browser is running or some malicious software is running, I elect, based on the design of the software, to not allow those things to ever communicate with that IP address and enforce only the VPN software. And then in addition, some other mitigations could be using authenticated DNS. That would have mitigated my DNS spoofing, so that would have been a great strategy. And then if you can pass the public IP in band instead of via DNS, that would also completely mitigate that attack. Now I'm going to conclude with this note that so HTTPS was a question that was raised, and absolutely that's going to be helpful, because if Sean is accessing, I'm sure he's getting tired of being picked on, by the way, but if Sean's accessing TD.com or whatever the FQDN is, of course that's going to be protected by SSL, right? They're not going to be serving a plain text version of TD.com. So that's great. That does protect the end user with a warning if this attack is being used. What it doesn't protect though is, in that instance, wouldn't protect from being eavesdropped. So in the the SSL handshake, of course, I'm still going to see that he's going to td.com. And if he's going to something maybe a little bit more off the beaten track, I could be using that for blackmail or something like that. So I still, not saying you are, Sean, but just an example, so anyway, these are just some of the ideas, but HTTPS absolutely is going to help mitigate a lot of this. It's just not foolproof, and it doesn't solve every edge case associated with it. Okay, we are over time, so I'm just going to wrap up. You can see I had a few more slides that I knew I was not going to get to. And to conclude, thank you so much for attending. This is us on that wonderful road trip I talked about at the beginning. Everyone's happy. We've avoided the detour completely with this awesome mitigation, and here we are. So appreciate everybody's time and effort, and awesome.